Welcome. In this video I'll discuss CGL MHD. And this is an extension of MHD which is often used in things like space plasmas, but also has some applications in magnetic confinement fusion, particularly mirror machines. And it's used to describe cases where the collisions are infrequent enough that we have anisotropic pressures. Because most of the time so far we've assumed that the pressure is isotropic. We've assumed that the pressure is the same in the perpendicular direction as the parallel direction, but this is not necessarily the case. So there are several different approaches to try and extend MHD beyond the high collisionality regime where it usually works. These include the CGL that we're going to discuss here. So CGL is one of them. There are extensions beyond this to try and capture things like wave particle resonances. These are called Landau fluid closures. And then there are things like kinetic MHD, which is a kind of kinetic equation, but it's in the MHD ordering. So it's a large length scale, high velocity, so thermal speed kind of closure of the kinetic equation called kinetic MHD. So we have CGL we'll discuss in this video, and then Landau fluid closures I might discuss in a future video. So these are all different ways of extending MHD, and in particular CGL, the extension is to the pressure tensor. So in particular we've taken P is a tensor, and in MHD we assume that this P tensor is just a scalar pressure times the identity matrix. So it's a 3x3 tensor or a matrix, and we've just assumed that it's P like this, and these are all zeros. Now in extended MHD we might add a stress tensor. So we might have the pressure tensor is a scalar pressure times the identity matrix plus pi, which is the stress tensor or the viscosity. And this typically has zero trace, so it has zeros or the elements along the axis on the diagonal add to zero. Might have off diagonal terms representing viscosities or FLR effects. You might have two fluid MHD, where you just split the ion and electron pressures. So we might have that P is the electron pressure plus the ion pressure plus any other viscosity effects. So these are, I'll underline these twice to make sure these are tensors, second order tensors, so matrices. So we have the stress tensors, we have ion and electron pressures, for example. Now what CGL MHD does is slightly different. So we split the tensor into two pieces. So we say that there's a parallel pressure, which is in the direction of the magnetic field. So this is on the diagonal, but it's in the direction of the field, plus a perpendicular pressure, which is in the directions perpendicular to the magnetic field. This might also be extended by adding an extra stress tensor too. And so now what the pressure tensor looks like is a 3. So let's say the parallel to Z is, let's say Z is the parallel direction. So this is along B. Then the other two components have P perpendicular. And then the off-diagonal parts may be due to the stress tensor. So when does this need to be used? So when is this valid? Or particularly when does the MHD approximation break down? So when can we assume that the pressures are isotropic, and when are they not isotropic? So the timescale for the parallel pressure to be approximately equal to the perpendicular pressure depends on the collision times. And so for electrons, for example, it's the collision time of electrons colliding with ions mainly, and for ions it's the ion collision time. So we've got ions scattering off other ions mainly. So we have tau e and tau I timescales for the two different species. So in the core of the plasma, core of a typical tokamak, you might have tau e is like 10 to the minus 4 seconds, and tau I is like 10 to the minus 2. So if we're interested in phenomena which are faster than this kind of timescale, which is most fluctuations, for example, are faster than this, then we have anisotropic. So in the core of the plasma, the timescales are quite long for this pressure to equilibrate, and so in general we can't assume isotropic pressure. In the edge of the plasma, it's a little bit better, but we still have the tau e maybe 10 to the minus 6 seconds or so. And so electrons may be isotropic. If we're typically dealing with frequencies which are less than a megahertz, but tau I can be sort of 10 to the minus 4 or so seconds, and so this may be anisotropic. So in the edge of the plasma, ions may be anisotropic with different parallel and perpendicular temperatures, whereas electrons typically would be isotropic. Okay, so what's the simplest way of trying to keep different parallel and perpendicular temperatures, which is what the CGL method is just a simple extension to MHD. Well, we think about what we do in MHD to get the closure, and we just essentially use that same method. So in closure in ideal MHD, we just assume the adiabatic. So essentially calculate the pressure by assuming that the plasma is adiabatic. And so just say that d by dt of p over rho to the gamma is 0. So p over rho to the gamma is constant, and so we have an adiabatic response to any fluctuations. In CGL, there's a small extension to this. We just, instead of having one equation, we now have two. And so this is sometimes called the double adiabatic closure. And we now have one closure for each pressure. So we have one for the parallel pressure. This depends on b squared over rho cubed. And then we have one for the perpendicular pressure too. So we have d by dt, and here we have p perp rho b or 0. And this is essentially the simplest model for parallel and perpendicular pressures, a simple extension to MHD. We're still assuming, so it essentially assumes no heat flux. So Q parallel is Q perpendicular is 0. So one interpretation of these closures is that these are conserving the adiabatic invariance. So we'll see a different derivation of this from a different justification next video. But for now we can consider what these mean physically. So this is essentially conservation of magnetic moment. And we can see this. So the first moment is conservation of magnetic moment. And you can see this by writing the pressure. So the perpendicular pressure is roughly like the average of the perpendicular kinetic energy. So it's the average of this v squared times the density, or the mass density in this case of the ions. So you have essentially the temperature times the density. Because these m's and 2's obviously are constants, then mu times b is roughly like v perpendicular squared. And so putting these together, you just have that the average of mu b times rho is roughly like p perpendicular. And so we have P perpendicular over rho B is roughly constant. So because it's some function of mu and constants like the ion masses. So that's the first one, is conservation of magnetic moment. Leads to this invariant on the perpendicular pressure. The second one is more difficult, so I'll write this out here. So the second adiabatic invariant is related to the bounce time between 2 points. So this is if you have a particle moving along the magnetic field between 2 bounce points. So it's just some kind of a bounce. And some kind of distance L along here. Some kind of distance L along here. There is a conserved quantity, or approximately conserved quantity on slow timescales of J, which is the integral over the whole orbit of the mass times the parallel velocity dl. So L is this distance here. So this is like dl. The distance along the path. So the integral of this m times v parallel over this bounce orbit is approximately conserved if the orbit changes slowly compared to the bounce time. And so we can estimate this and relate this v parallel to the parallel pressure. So we say that the parallel pressure is related to the average of v parallel squared, just like the perpendicular pressure times the density. We're calculating this length here, which we'll use to estimate this integral here. So we just say that this integral is over a length dl, which is the length of this bounce orbit here. So that J is roughly like a mass times a parallel velocity times a length L, which is this bounce. And then we assume that essentially particles are trapped inside a flux tube. So we have a tube which has some cross-sectional area, set area A. And there's a magnetic field through this tube, which is B. Now because the flux is just area times strength of magnetic field, this is constant. If this is a flux tube, then the flux inside the tube is conserved. So then we consider that we have a tube of plasma, and we consider a group of particles which are trapped inside it. So the mass of particles which are trapped inside. So this is roughly like the density times the length times the cross-section area. So it's the density times the volume of this tube. And we assume that this is constant. So as the tube is moving around, the particles, the total content of this flux tube is constant. And then we just rearrange this here so that using this conserved flux, we can relate A here, we can relate this to B. And so we end up with that L is roughly, so it's 1 over rho A, just moving this over here, and this is roughly B over rho by combining it with this flux conservation here. And so now we can combine the length is B over rho with the definition of the parallel pressure here in terms of V parallel, and put this into here. So we can use this expression here to say that V parallel L is roughly constant. So we can combine this expression from the adiabatic invariant that V parallel L is roughly constant. We put this L into here, and so we have that V parallel times B over rho is roughly constant. And now we can combine this expression here for V parallel into this expression here for P parallel. So we take this and put it into here, and what we end up with is that P parallel is roughly now a V parallel squared. So this is like a constant times rho squared over B squared times this rho here. and so this is times some constants. And so we can write down that just move this over to the other side. So we have that p parallel b squared over rho cubed is a constant. The constant will depend on many factors. So we have things like the mass, this conserved quantity j, so the adiabatic invariant. The point is these are all slowly varying. And so if there's a class of trapped particles which are trapped inside a flux tube, if the flux tube is slowly moving so that this adiabatic invariant is conserved, then we have this expression here for the adiabatic constant here for the parallel pressure. And then, so this arises from the conservation of the second adiabatic invariant. And using these closures, so d by dt of this is constant, so d by dt of this is 0, and d by dt of this up here is also 0, so time derivative of that gives the CGL equations. And these I'll just write out the end here so you can see them. So this is a set of equations for each species S. So S here is labeling the species. So in principle you have one set of these equations for the ions and one set for the electrons. You can then also do a cold electron version, which is the typical one, where you assume the electrons are zero pressure, or you can also assume the electrons have an isotropic pressure, because as we saw at the beginning, the electrons tend to be more collisional, and so tend to have a shorter collision time to be scattered between parallel and perpendicular temperatures, whereas the ions are most likely to have the anisotropic pressures. But you end up like MHD or the two fluid equations. You end up with a density equation for the density of species S, the flow velocity, and the parallel and perpendicular pressures for each species. And then this pressure here, this here is the tensor. So this is p parallel times the b vector, so dyad, plus the perpendicular part. And this would be identity minus bb. And then optionally, this could be, you could add in the extra terms if you want the FLR corrections. So this would be FLR, so the gyro radius corrections. Okay, so next video we'll go through and derive this in a little more detail, or at least show how it can be derived from the Vlasov equations.